Okay, so I want to do a quick recording on the homework question that we were looking at last week. So apologies if my voice is a wee bit rusty. I'm still a bit ill, but hopefully it's clear enough to explain this video. So what we have are 4 forces. I'm going to label them just to make experience a bit easier. Up here is force 1, force 2, force 3, and force 4. So we've got 4 forces acting on this object, and we're being asked to determine is it in equilibrium or not. So for equilibrium, remember there's 3 conditions. So those 3 conditions are: the sum of your forces in your horizontal direction must equal 0, sum of the forces in your vertical direction must equal 0, and the one a lot of students forget is the sum of your moments must also equal 0. So let's look at examining these 2 things first. So I want to break all of my forces down into either horizontals or verticals. So I'm going to redraw my shape here fairly quickly, and I want to examine the forces. So remember, resolving a force, I have a force that looks like this, 10 newtons, and I want to resolve it into horizontal and vertical components. What that means is I want to resolve it into horizontal and verticals that act the same way as that force. So instead of having that 10 newton force acting at an angle, I think our angle here is 10 here. I'm just going to redraw it. Oops. It's not letting me erase it for whatever reason. Okay, so instead of having that force of 10 newtons acting at that angle 10 degrees, I'm replacing it with a vertical force, my force vertical, and a horizontal force horizontal, that act the same way. So imagine I had a boulder down the bottom here. I could push it with 10 newtons at 10 degrees and get to here, or I could push it vertically this direction and then horizontally over. I'll end up in the same place. That's an easier way of thinking about it. And we have formulas, we've proved these before. My force horizontal is os F cos cosine the angle. My force vertical will also be F sine the angle. Okay. So we're going to want to break every one of these 4 forces into force horizontals and force verticals. So we're going to have a force vertical, force horizontal. This force, because it's a pure horizontal force, won't have vertical. This force will have a downward vertical and a horizontal to the right, and this is a pure vertical, so it's only got a downward force. Okay, try and squeeze it all into one screen. So now if I want, I can create a small little table. F1, F2, F3, F4. Okay, so I'm going to put my moments in the same table, but for the moment, I'm going to have my force horizontals, which are always F cos theta, force verticals, which are always going to be F sine theta. So I'll do the first one, then I'll pause the video and fill them in. Just double check that you know where these are all coming from, so that you can do them yourself if needs be. So for that first one, F cos theta, I look at F1 and I have a force of 10. So it's not going to let me move any too easily. Okay. So F1, force horizontal of F1 is equal to F 10 cos theta. My angle is 10, and that will give me 9.81. Now, just be careful. This force will be traveling to the left, so it's going to be negative. So that's where that negative comes from, but I have negative 9.81. I do the same for force vertical. So force vertical, F1 is 10 sine theta, which is 10, and that will give me 1.74. And look, it's positive because it's going upwards. So $1.74. I'm going to pause this video and fill in the rest of this table. Just take a moment yourself and check these afterwards to make sure that you know where these values come from and that you can complete the table by yourself. Okay, so this is where we would get. So the sum of my horizontal forces is 7.26 and the sum of my verticals is minus 1.19. So if I check my conditions for equilibrium, some of the forces horizontally don't equal 0, some of the forces vertically don't equal 0. So I know this thing isn't going to be in equilibrium, but I'm going to check the sum of the moments as well, just to guarantee it. So remember, a moment is equal to force by perpendicular distance. So let's examine our forces. Okay. In our moments calculations, I ignore the sign of the horizontal force. What I'm going to put a positive or negative sign on is if the moment twists me clockwise, I'm going to take that to be positive. If the moment twists me counterclockwise, I'm going to take that to be negative. So let's look at this first one again. I have 9.81, which is this force here, times the perpendicular distance to point A. So I have a horizontal force, that means I need a vertical distance. It's going to be this distance here. If I come up and read it, it's 1. So 9.81 times 1. So it's going to be 9.81. Is it positive or negative? Well, if I'm fixed here at point A and I'm twisting, only looking at that other force, 9.81, it's going to twist me this direction here, which is counterclockwise. So that's a negative. So it should be negative 9.81. Okay. So I'm going to update this. 9.81 times 1. 9.81, and it's going to be negative 9.81 because it's a counterclockwise moment. Okay. The vertical force, 1.74. It's a vertical force. There's no horizontal distance between it and A. They're on the same line of action. So look, there's no horizontal distance between it and A. So that would be 0. Doesn't matter what the force is, it's going to be 0. There's no moment happening there. Okay. My next one, I have F2 here, which is 10 newtons. It's a horizontal force, so I need a vertical distance. It's still 10 away, it's on that same plane, but this one would twist me clockwise. So this one's going to be 10 times 1, and can be a plus 10 Newton meter moment. There's no vertical component, so that's 0. Now on to this one, F3, this force here. Okay, so it's 7.07 times. Now that force, even though my hand's a bit crooked, is on the same line of action. It's a horizontal force. There's no vertical distance between it and the point, so times 0. There's no moment there, and the last one is 0. Okay, so the sum of my moments here horizontally is minus 0.29 Newton meters. Okay, I've only got 2 other moments to go and solve for. One of them is this. So this was 7.07. 7.07. So it's a vertical force. I need a horizontal distance. There's a clear horizontal distance here, which is 2 meters. taking that 2 meters from my original drawing, by the way. Up there. 7.07 times 2. 14. Okay, and then the last force is acting straight at A. It's a vertical. There's no horizontal distance, so that's 0. So this moment is 14.14. So to sum my moments, I just add them together. 14.14 minus 0.29 gives me 13.85 Newton meters. Okay, so that means that this shape, if I go back to the start, all these forces are acting on it. These forces result in a horizontal force like this acting on it, and a vertical force upwards. So in reality we have a resultant R acting like this, and that resultant in reality is causing a clockwise twist of 13.85 Newton meters. So because my force horizontals don't equal 0, my force verticals don't equal 0, the sum of my moments do not equal 0, I can say that this shape, or this object, is not in equilibrium. Why? All three conditions must be met. None of the three in this system are met. So my force horizontals do not equal 0. My sum of my force verticals do not equal 0. And the sum of my moments do not equal 0. So it's a nice little question. Hopefully it helps some of us. You could, in theory, get to saying, okay, well, my force horizontals don't equal 0, and say it's not going to equal equilibrium that way. Better off just finish off the question as a nice little refresher how to do it all. Hopefully most of us determined that it's not an equilibrium. And yeah, we're going to take what we've learned in here and what we've learned the last 4 weeks, and we're going to get on to simply supported beams. So it's a lot of the same idea. You have forces and moments, and we'll talk about that next week. But if you have any questions on that, feel free to drop me a message on Teams and I'll come back to it.